Hello, nice to see you again. Today, we're going to continue our lecture. It's so unfortunate that we have yet to be able to meet, but we'll continue our materials anyway. Uh, yeah, good to see you again after the midterm exam. And I know that this semester we have a shorter period than we expected before. So without further ado, let's delve into our materials. Okay, so our discussion today would be about the still a continuation on the credit risk theme, but today we'll see the portfolio side. I think before the midterm exam, we have seen the credit risk for individual assets, and as you know, and we have discussed, like a financial institution will have portfolio of loans, uh, which means portfolio of assets. Uh, that they lend out to corporations, to businesses, and all other entities. So today we're going to see the uh, portfolio application on the credit risk. I think you have studied also, you have learned in another course like portfolio theory and management uh, that teaches you or that leads you into the discussion on the use of portfolio. Why do we need portfolio? Um, how the portfolio can benefit an institution or even an investor to reduce the risk, especially or in particular the specific risk. Okay, so we'll see some models of loan concentration here today before we go into the portfolio theory. So you can see on the slide risk rating at the beginning of the year and then risk rating at the end of the year. So it's quite uh, it's not surprising at all to see that a triple A loan most likely or has a chance of 85% to be still having a triple A rating at the end of the year. And you can see that the triple A that might become or might be default at the end of the year has a chance of only about 1% based on the based on research and the previous data or previous database. On the other hand, if you see the triple C, triple C, the chance of uh, no, getting into a triple A rating will be relatively low, at 3% only, uh, while the possibility of default is about 4% at the end of the year. So this is quite appalling because in the portfolio context, if you see this data, uh, it turns out that actually if you have a portfolio having uh, most like triple A loans with some of the not so good loans, it's probably acceptable because if you notice that the possibility of getting default even for the triple C is only 4% after 1 year. So if you have a portfolio consisting of let's say 80% or 90% of good or investment grade loans, well the other 10% or maybe 5% is comprised of, for example, the not so good or like questionable loans. At the end of the year, or if you don't give the loan for such a long period of time, that might be that might be acceptable or relatively acceptable. So, of course, we don't recommend financial institutions to do so, especially for a longer period of time. But again, for the short period of time, this might be, uh, yeah, I mean, you just, or in other words, you might get out of the year uh, not having bankruptcy or not having big trouble at all. And then I think this is in a similar fashion, we can see this one, risk rating at the beginning of the year and risk rating at the end of the year. If you see, so quite the same story here, 95%, 1%, 3%, 4%. Okay. So this is another, we'll go into the first model, I think the long concentration model. So see here, the concentration limit that you would allow could be estimated as the maximum loss as a percentage of your capital, right? And then multiplied by 1 divided by your loss rate. So we'll see an example here. Let's say management caps losses at 15% of your financial institution capital to a particular sector. Let's mention randomly a sector, maybe agriculture or manufacturing or anything. And your team, your internal team estimates that amount lost per dollar. So amount lost per dollar, we could call this one the loss given default. We can call it LGD, loss given default is like 40%, right? 40 cents per dollar. So it's about 40%. So you could estimate the concentration limit that you might allow. So this would be maximum loss. Again, you have capped this one as 15% of your financial institution capital. So 15% multiplied by 1 divided by the loss given default. Loss given default. So we get the result of 37.5%. So you would want to limit, right? The concentration into a particular sector by 37.5% in this example. Okay, now so we'll review the modern portfolio theory. This is a very interesting topic. Again, this is a subject of its own, a big topic actually, and I think it's actually quite out of our coverage to discuss it too far, but nonetheless, I think we have to discuss a bit about the modern portfolio theory. Okay, so you might have learned this in, again, the portfolio theory and management course, but let me review a little bit. In 1951, so there was a brilliant guy named Harry Markowitz. So this guy went to the University of Chicago and completed his undergraduate program in mathematics. And then he continued his graduate program in economics. And as we know, the University of Chicago has so many, the legends, like legendary economists, the Nobel Prize laureates. So he was under the supervision of Jacob Marshak. And then in 1951, he defended his dissertation. And one of the examiners was Milton Friedman. So it's a very interesting story that he told, I think, in his biography, that Milton Friedman, I think, gave certain comments that made him a bit nervous. I would say, so during his graduate program, his doctorate program in economics, and the dissertation that he wrote, he was interested in the capital market phenomena, how to apply the mathematical economics, as right now we know as a mean variance model of Harry Markowitz. So he applied that to the capital market setting, So that was, I think, one of the trailblazers, because before Markovit's time, we only knew that there was like economics. It had been there, yeah, long before Markowitz took his graduate program, economics, and also we had some sort of accounting. I know it uh, was not modern accounting that we know right now, but it was sort of bookkeeping. But again, it was, yeah, we could say it's accounting, typical accounting and economics. So economics again was traditionally dealing with the use of mathematics to solve economic problems, and accounting predominantly dealt with bookkeeping at the time. So before Markowitz has had his dissertation examined, so we had economics and accounting. But again, the capital market, to apply the mathematical equations and formula to the capital market was relatively new at that time. So Milton Friedman gave quite interesting comments, and he was saying that this dissertation is not economics, this is not business administration, and this is not literature either. So that made somehow that comment made Harry Markowitz a bit nervous, and then he got out of the dissertation room. But in after a certain period of time, a couple of minutes, maybe about half an hour, he was called back to the room, and Milton Friedman congratulated Harry Markowitz. So he became a PhD again in economics in 1951. Interestingly, in 1952, this paper was published in the Journal of Finance. As we know, Journal of Finance, even until today, is a top publication, one of the best, if not the best, in finance and economics. So he published his dissertation as a paper titled Portfolio Selection. So that again, that became, I think, the trailblazer, and he would be known as the father of modern portfolio theory. And even we could call him the father of finance, or the father of modern finance, because that was, I think, the first time we recognized and also admitted that now finance uh, had become like a science, and also an applied science of its own, combining a lot of traits of economics, a lot of techniques from economics, but also a lot of characteristics of accounting. So that's about a brief history of the modern portfolio theory. Of course, afterward we have many other brilliant people like William Sharp, and then Gene Fama, and all other new generation finance experts and Nobel Prize laureates. But again, our focus is on the traditional or the modern portfolio theory. Firstly, uh, proposed by Harry Markowitz. Okay, so when we talk about the modern portfolio theory, actually, we could imagine that the portfolio, what's the meaning of portfolio itself? So portfolio means, as you know, portfolio is defined as a collection of something, right? Collection of something. So if I say a portfolio of assets, that would mean a collection of assets. Portfolio of assets means a collection of assets. Portfolio of stocks would mean a collection of stocks. So portfolio is definitely is defined as a collection. So it's more than one, right? More than one thing, or more than one asset there. So we'll use the simplest example where we have only two assets. So I would like you to imagine a situation, say um, maybe a certain certain person, say Anna. Okay, so let's say Anna is making a cake, right? It's making a cake. Uh, for the sake of brevity, to make the case simple, let's imagine that she only has two ingredients, two types of ingredients. Again, this is to make to just to simplify the story, right? So the first ingredient is like sugar, right? So she has sugar and she has salt. So it's very, I know it's quite a strange example, but you can imagine that. So if she is to make a cake consisting of 100% sugar, right? 100% sugar. So can you imagine the taste? So the taste of the cake would be 100% sweet, right? What about if she's using 100% salt, then the taste would be entirely salty. Right? So another example, what about 50%? Right? 50% sugar and 50% salt. So it sounds quite awkward, but this would produce what, like 50% sweet and 50% salty. So, and the essence of the story is that if we make something, we make like a melting pot of something. Uh, yeah, our conventional or logical uh, conjecture would be like the thing will have like the combined taste, right? Combined components or materials from its components. Okay, so let's put this into the portfolio concept. So let's imagine now you have two assets, right? Two assets. Let's say assets number one and asset number two. So we have two assets here. Okay, so I could say that we have like when we have the first asset, so we expect something, right? So we have the expected return on asset one. And then the second one, sorry, we have the expected return on asset two. So, um, so when I combine these assets into a portfolio, so I could make a conjecture like this, right? So expected return on the portfolio consisting of two assets should be what? Should be the weighted average of individual assets expected returns. Again, this idea, you remember the example, I remember our example about the making of a cake, right, consisting or comprised of two ingredients only. So again, coming back to that example, we could apply it here. So this is our conjecture, our hypothesis. Right? So this should be what? Should be the expected return on the first asset plus the expected return on the second asset. But before adding them, of course, we have to multiply each of them by its respective weight. Again, the weight, remember our story, maybe we are using like 90% the first ingredient and 10% the second, or 50-50 or 70-30 or so forth. So we have the first one here, the weight of the first asset, and here the weight of the second asset. So we could write it this way mathematically. So expected return on the ith asset multiplied by its weight, right? Each weight, and then we sum them together. So we're not going into the proof, right? Not going into the proof, but as you might have taken the portfolio theory course, you know that this conjecture is true, right? This is true, right? This is the truth. So we could conclude that the expected return on a portfolio is merely the weighted average of individual assets' expected returns. So nothing special there. So it could be logically thought about, logically like, uh, made and confirmed, right? So this has no problem. So again, one more time, it has been proved, right? You can try it by yourself, having that two assets with with their series of past returns. You can combine them into a portfolio, and you find out that again, the expected return on portfolio is merely the weighted average of individual assets' expected returns, just like the example of cake making that we had just now. So nothing special there. So what about the portfolio risk? So we could guess, or again, we could conjecture that in a similar fashion as the case of expected return. So we have the portfolio risk, maybe from the variance, but we could go in directly to the standard deviation. So you notice here is a mean here, expected return is mean, and then the standard deviation here, or the square root of variance, is the representative or the proxy for portfolio risk. So again, we could conjecture here, we have two assets. So this could be what the risk of the first asset plus the risk of the second asset. And then each risk is multiplied by its respective weight. So again, what is our conjecture here? So we conjecture that the portfolio risk should be the weighted average of individual assets risks. Right. Okay, so we could write mathematically the um, standard deviation, or the risk of the ith asset multiplied by its weight. And then we sum them together. Okay, now again, in the portfolio management, in the practice of portfolio, we know that, is it correct? No, it's not. And it's good news, right? So we know that this is not right. Why is it good news? Because the real portfolio risk, the resulting portfolio risk, would be lower than this, right? Would be lower than this conjecture, or this hypothesis. It's lower. So again, uh, if we find a certain number here, the real portfolio risk would be lower than this one. And then the gap between the real number and the conjectured number is named the benefit from diversification. So the real number will be lower than this one. Of course, again, we're not going into the proof, because we are not, again, our theme today, or our main interest, is not on proving the portfolio theory, but we borrow the modern portfolio theory to show, or to estimate the credit risk, right, for a portfolio. Again, one more time. So this is not right. So what's our conclusion here? Portfolio risk is not the weighted average of individual assets risks, but should be lower than the real one, right? Should be lower than the real one. So again, the gap of the real one compared to the conjectured number using this weighted average method is called the benefit from diversification, the benefit from portfolio. So how should the portfolio risk be estimated? So we'll follow the Markovian method and the full method before William Sharpe came into this came into the came into the scene with uh, this capital asset pricing model about 1 decade later. Okay, so quite simple here. So let's make the notation first. So we have what is the return on the first asset? Return on the first asset, we can write it as R1, right? And we have return on the second asset, right? We also have the expected return on the first, oh, sorry, expected return on the first asset. And we have the expected return on the second asset here, okay? So going back to the logics right above, so we could write the portfolio return, right? This is a historical or ex post, right? Ex post measure. A portfolio return, if we have like two assets, it would be what? Would be return on the first asset plus return on the second asset, and each multiplied by its respective weight, right? What about expected, right? Expected return, okay? So this would be expected return on the first asset plus expected return on the second asset, right? And each again multiplied by its respective weight. Okay. Okay. Now I want to bring you back into a certain statistical concept. I mean, if you remember, so if we have like expected, right, the value of something minus the expected value of that thing, what is it? Do you remember? This is the average, right? This is the mean. Okay. What about this? The expected value of something minus the expected value of that thing squared. Of course, this is what? Variance. Okay, so this is what we want, right? So we will adopt this technique. Okay, so what about if I say, so I want to know the expected, right, return on a portfolio minus the expected return on the portfolio squared. So this is what? The variance of the portfolio return. This is what we are looking for, right? The risk of the portfolio. Of course, later we have to find the square root of it, right? The square root of variance is the standard deviation or the proxy for risk. But you see the logic there. So now we'll start deriving the formula from there. So expected, right? Oh, again. So the variance of the portfolio return, is it again? We write it again. So expected, right? Return on the portfolio minus expected return on the portfolio squared, right? So now let's make into detail. What is again the portfolio return? We see it here, right? This one. So it's a return at return on the so return on the first asset plus return on the second asset, right? Multiplied by its respective weight, right? So minus. So what's it? What is the second item there? Second component, expected return on a portfolio. So this one, expected return on the portfolio, right? pretty much the same, but now we have, so to be careful here. So expected return on the first plus expected return on the second, right? And then we multiply each by its respective. Okay. Okay, one more. Yeah, square. Okay, so based on your mathematics lesson in high school, you still remember, so we see similar things here, right? Weight one, right? We have weight two and weight two. And be careful here is minus and also minus, right? See the brackets there, right? The brackets. So it's minus, right? Minus, minus. Okay, so we should combine the like same components. So we see here weight one, right? The weight one. So here is return on the first asset, right? But here is expected return on the first asset. But remember, this is minus, right? So be careful. Okay, what about the second one? Plus weight two, right? The weight two. Here is return on the second asset minus. Here is expected return on the second asset. Okay, close it. Of course, we close it square. And remember, this is minus, right? Minus here. So minus. Okay. Okay, now we have a situation again similar to your um, algebra lesson in high school. We have, let's imagine that this is A, this is B, right? So A plus B squared. So remember, A plus B squared would be A squared plus 2AB plus B squared, right? So put it down here, expected. So we put, this one is A, so we do it first for the, like, this part, the first component here. So W1 squared, and then 1 minus expected return squared, right? Okay, plus this one, maybe W2 squared expected return on the second asset squared, right? Plus now 2AB, right? So 2 W1 return on the first asset minus expected return 1. Then W2, oh, let me write it so it's easier to imagine. So see, this is 2, right? 2 multiplied by this one and then this one. So I can write it this way, right? 2 W1 W2, right? And then return on the first minus expected return on the first, then multiplied by return on the second minus expected return on the second. Okay, so it's almost done. Okay. Now, you see here, there is an expected sign. It's very similar, similar technique as the sigma theorem. So we have to put the expected into each item. So So I want you to imagine again the situation. I think you studied this before in your statistics courses or maybe mathematics courses. So expected value of a constant is the constant itself, right? So if I ask that, what is the expected value of 5? The expected value of 5 would be, of course, 5. Right? But the expected value of a random variable would be the expected value of the random variable. So let's put into practice now. So expected, right? The first one, expected value of W1 squared should be what? This is a constant, right? So W1 squared. Expected value of this is a random variable. So again, it remains the same, right? So expected value of the random variable. Okay. What about this one? Expected value of W2 squared is a constant. So again, this would be the constant itself, W2 squared. But the expected value of this one will be the expected value of that one because it's random variable. So expected value of the random variable itself. Okay. Next, what is the expected value of 2? Of course, 2, right? What is the expected value of W1? Of course, W1. What is the expected value of W2? It's W2. What about the expected value of this? Again, a random variable, then the expected value of, and the random variable. Okay. So we're almost done again. So I want to remind you again about this one. How do you still remember? If I say, so expected, again, this is like a repetition, right? Expected value of something minus expected value of that thing squared is the variance, right? Variance of that thing. So if I'm saying, so now you can imagine, what if I say expected, right, return on the first asset minus expected return on that first asset squared. This is what? Right, following the previous analogy, right? This is corresponding to the previous example. This would be what? The variance of, the variance of the first asset return, right? Okay, I hope you follow this. So now we could put this into again practice. So W1 squared. So this would be the variance of the first asset return, right? Plus W2 squared. And what is it? So similar pattern you see there. So the variance of the second asset return, right? So plus that 2, weight 1, weight 2. Now this is quite special. I hope you remember from your statistics lessons or courses. This is called what? This is called covariance. This is so the covariance between the first and second asset. Okay. So this covariance, you know that again we are not going to prove any or discuss two details about portfolio theory. Covariance between asset 1 and 2 could be estimated as the correlation coefficient between the first and the second asset multiplied by their standard deviations. So standard deviation of the first and standard deviation of the second. Okay, so we'll do it that way. So we'll interchange this one. We'll change this one to the correlation between the first and the second multiplied by the first standard deviation and the second standard deviation. So going back to our story here, this is the portfolio variance. Right, this is again the legendary formula, mean and variance model of Harry Markowitz. Hope you remember. Right? Of course, have to find the square root of this one, right? So we just need to take the square root of the result. Right? Okay, so this is, I think, the explanation on again the formula. Properly. Okay, so we got it. Again, we find the square root of the portfolio variance and you will get the portfolio standard deviation or the portfolio risk. So what is the main purpose of making or forming a portfolio again? Is to reduce the risk, especially the systematic risk that could be diversified away, could be minimized or even eliminated using the portfolio. However, the systematic risk cannot be diversified away. That's why we need, again, the hedging techniques. We need the internationalization to further reduce the systematic risk. And of course, we'll talk about the hedging process, hedging mechanisms throughout our course here in risk management. So we see an example here. For example, we have two loans. The first loan has the proportion of 40%. The second has proportion of 60%. The first loan has expected return of 10%, the second 12%. And then the first loan's risk is estimated to be this much and the second this much. And we find out that the correlation between the two assets is minus 0.84. I you still remember from the statistics course or courses in the correlation coefficient ranges from -1 to 1. So the sign minus or plus signifies the direction of the move, right? So if it's positive, it means that the two things move in the same direction. However, if it's negative, then one thing and the other will move in different directions. So here, obviously, minus 0.84, that they move in different directions. However, the number or the amount of the coefficient signifies the magnitude of the relationship. So it's between, again, it ranges from -1 to +1. So here is minus 0.84. And here's the covariance. I hope you still remember. Covariance is can be estimated as the correlation multiplied by the first and then the second standard deviations. So we put into our, again, the modern portfolio theory. So this is a weighted average, remember? The weighted average, right? So 40%, this is the weight of the first multiplied by the expected return on the first asset plus the weight of the second multiplied by the weight, multiplied by the expected return on the second asset. However, for the portfolio risk, starting from variance, we have to use the mean variance model of Harry Markowitz that we just saw in our whiteboard, on our whiteboard, right, this one. Okay, so we put this into our case. Okay, and then we get a variance of this much, so it's like 0.12%, right? 0.12%. And then of course, the portfolio risk would be the standard deviation of the portfolio return, or the square root of this, the square root of this one. So we got 3.53%, right? So if we are based on our conjecture, or let me rephrase my statement again. So if we try to find the portfolio risk as the weighted average, right? Weighted average. So we can calculate this as what? 40% multiplied by this one plus 60% multiplied by this one. So this is a weighted average that we conjectured before. So let me calculate using my calculator. So it's 40% times 60% times 0.0980. So we'll get 9.3%. Wow, you see the big difference there, right? So if we calculate this using the weighted average method as we conjectured before, we would have gotten 9.3%. But you see the reality or the real measure is only 3.53%. It means that the difference, the big difference there, 6%, about 6% difference, the difference is the benefit from the portfolio, benefit from diversification. Cool, right? So, right, uh, so we only get about one third of the full measure, right, as we conjecture. So again, this is the benefit from diversification. So this is still remember from portfolio theory and management. This is the efficient frontier, right? Efficient frontier. This is a uh, global minimum portfolio. And this is the efficient frontier. We talked about this in the portfolio theory class, so we're not going to repeat that one. Okay, so this is the if we apply this to many assets. So far we harness an example of two assets here, but we could extend this to three assets, five assets, 30 assets, and so forth. And of course, as I alluded to at the beginning of our session today, that in the coming decades, sorry, decades that came later, then came other, scholars and finance experts, other economists. That would improve, uh, the application or uh, the portfolio techniques. William Sharpe with his capital asset pricing model, and other asset pricing models by other experts. So, but for this one, let's extend it to many assets. So we could write this way, right? The variance. So we have two components here. This this is the first component, and this is the systematic component. Right? So the first component we can write easily. So we have what? We have the variance of the ith asset multiplied by its respective weight squared, right? So we sum together. Now the second one, so we have what? We have the weight of the first, we have the weight of the pair, we, we can call it J asset, right? So we have the correlation of each pair, right? So we have the I and J. Now we have two, right? We only have two in pairs. So we have two, will be like I and then J. Okay. So you see it here. Okay. And of course, I is not equal to j. We can write there also. Right, so I is not j. Okay, for the case, yeah. Okay, so if you have questions, we can discuss it again online. We can talk on like any communication means that we could access. So we'll continue with Moody's Analytics Portfolio Manager. So here we have again the measure or the proxy for expected return, the proxy for risk. Right? So AIS means all-in spread. So you could imagine all-in spread means the spread, right? Spread between what a financial institution could charge from its clients and the cost of fund that they have to procure, maybe from depositors, from uh, issuing bonds from other sources. But again, this is the spread, right? All-in spread. Okay, so all-in spread. We have all-in spread minus EDF. This is expected default frequency. So expected default frequency. So what is the possibility of going down, right? Possibility of going to a default situation. And this is LGD, loss given default, right? Loss given default. So if it defaults, how much loss will you suffer, right? How much loss? Maybe like in our previous example, we saw like 40%, it might be 50%, might be 90% or whatever, right? So what about the risk measure, risk proxy? This could be measured as this one, expected default frequency, again, the possibility of default, multiplied by 1 minus expected default frequency. So obviously this is what the probability of not getting default. And then we find the square root of it, and then we multiply the result by loss given default. Okay, so we'll see an example here. See an example for the first asset. So we see the story there. The first asset constitutes 60% of the portfolio, and then the second is 40%. So annual spread between, again, see, loan rate. So this is a loan rate that we charge, or the financial institution charges to its clients, and its cost of funds that it has to procure. So the spread is 5%. So just imagine, for example, for instance, if the financial institution is lending money to corporations and it might charge like 10%, but when it had to raise, when it has to raise funds from depositors and other funders or other fund sources, it has to pay maybe 5%. So the spread is about 5. But in addition, it also charges annual fees. This is like good news to the financial institutions because they could earn more. So 5 and 2. So now it has 7, right, in total. That's why we call it all-in spread, right? The spread plus the annual fee. So 7%. Now, what is it here? Loss to financial institution given default. So this is the LGD, right? Loss given default. And this is the expected default frequency. So the probability of default. The first asset has a probability of default of 3%, and the second 2%. So we put into, again, the formula there. Remember the formula here. So to estimate the expected return of on the first asset, this is what the all-in spread minus expected default frequency multiplied by the loss given default, right? So 7% AIS, right, minus, this is the expected default frequency multiplied by the loss given default. So we get 6.25% for the first. And what about the second one? So second one, See, 4.5% the spread, and this is the annual fee. So in total, we have about what 6% minus expected default frequency multiplied by the loss given default. Again, loss given default means if the loan defaults, how much loss will we suffer? Right? So 25% for the first asset, 20% is estimated for the second asset. And then we also estimate the risk of each loan. Again, based on the Moody's technique, this is what the EDF multiplied by 1 minus EDF, and then find the square root of it multiplied by LGD. So for the first one, you see, expected default frequency is 3%, multiplied by 1 minus the expected default frequency, and then we find the square root of it, multiplied by loss given default. So we get 4.27% for the first asset, right? The risk of the first asset. And then the second asset, again, this is expected default frequency multiplied by 1 minus expected default frequency, find the square root of it, multiplied by the loss given default, and we'll get 2.8%. Okay. And then we put into the Markovitch mean variance model again, right? The expected return on the portfolio and then the portfolio variance. And then we find the square root of the portfolio variance, we get the portfolio risk at 2.52%. Okay, so quite interesting. The Moody's Analytics has its own techniques. Of course, every company, every financial institution will have its research division. They continuously conduct research, trying to find new techniques, new formulas that could give them competitive advantages to, of course, to gain more profit, but also to defend itself against new types of risk. So I think once they have the new techniques from their research team, then they could share, where they could publish their existing or the previous versions of the techniques. So we could learn it. But in essence, every financial institution will keep developing new techniques from time to time. Okay, so partial applications of the portfolio theory. So how do we get information? We in the United States, uh, all financial institutions will submit like core reports, every quarter. They'll have the data on shared national credits in every country, commercial databases. Have the SDC and other databases that could be subscribed to. So we could also find the deviation or the variance of a particular bank or financial institution compared to the national level, numbers or something. We'll see an example here. We have two banks here, banks A and B, 4 types of loans. See here, this is national average, right? We could say like industry average, and each bank has different characteristics. You see, the bank A has like predominantly this one, real estate loans, has given a lot of real estate loans compared to bank B. Bank B is giving more individual loans, right? So they have different characteristics. And then of course, we could use the variance techniques again, right? This is a national This is from the Bank A, Bank A figures for all the loan components, right? So we find here the variance, and then this is for the Bank B, right? And then we find the standard deviation. Uh, so this is not, it's not going to be used as like judgment, or it merely functions as a quick evaluation what's happening to the two banks. For example, the first one to the first, we don't see the, sorry, yeah, this is the second bank, right? Bank B has a standard deviation of 26.69% compared to the national average figure. But the first one, we don't see the standard deviation of this one. But so let me calculate quickly. So 0.055. So the square root of this is 23 point, so the square root of it is 23.45%. So you could see, compared to the second bank, Bank A has lower standard deviation, lower deviation compared to the national figure. But again, this cannot be used to say that is the Bank A is better than Bank B or the other way around. This is just to show that the level of deviation, their level of deviation, the levels of deviation compared to the national figure. Okay, so the last part of this section, and yeah, it's quite good. So we have discussed about 1 hour, so it's a good time. So this is to use the regression technique, right? The regression logic. So imagine the dependent variable here, dependent variable. So the dependent variable is the sectoral losses. Let's take an instance of this, maybe again, manufacturing or agriculture, right, or transportation or anything, right? So sectoral losses in ith sector uh, as a proportion to the total loans to that sector. So it's like the ratio, right? Ratio of the losses in the ith sector to the total loans given to that sector, right? This is the dependent variable. And then the independent variable would be the total loan losses. So this is like losses to all sectors, right? Divided by the total loans given to all sectors. So we regress them, right? So the ratio of sectoral losses is regressed on the ratio of the total loan losses, right? So we get the alpha and the beta. So we see an example here. So the data, you can see the data here. Uh, let's take one by one. Let's say this is the first dependent variable. So this is what commercial and industrial loans. These are our data, the previous data from 2015, from 2006 to 2015. And then we have the independent variable here, the total loans uh, ratio, again is ratio, the total loans, sorry, losses, total losses given to all loans to all sectors divided by the total loans given to all sectors. Right? So we regress this one on this one, right? Then we get, yeah, this one. So the alpha is 0.003, the beta is 0.75. What about the second one? The dependent variable is consumer loans, uh, the loss ratio, right? So the loss losses in the consumer loans divided by total consumer loans given. And then the independent variable remains the same, is the total losses given to all loans divided by total loans given to all sectors, right? So we regress this one on this one, right? Then we get this one, we get here. The alpha is 0.005, the beta is 1.25. Okay. Now, if you believe in the, again, when we discuss the econometrics, of course we have a lot of like assumptions and a lot of examinations to be done. We have to check again the classical assumptions, whether they fulfill the OLS, right, requirements, whether they are blue, right, whether they are best, linear, uh, and other, requirements. But again, we are not going to emphasize those facts, but we just simply use the regression technique, right, to get again the alpha and the beta. So if you believe in the regression, again the regression coefficients produced by our previous regressions, then you could apply this one when, for example, a potential debtor, right? Potential debtor comes to your bank, comes to your financial institution, then you could apply this one. You can check. So if the potential debtor comes from the comes to borrow money in the CNI component, CNI category, commercial industrial, then you know that the loss rate, for example, for this year or for this period will be about 11.55. How do you get this? And it depends on this one, right? The independent variable. So the independent variable, uh, so we could see here, loss rate for the company's loan portfolio. Right? So this is for the sector, right? This is for the sector. This is for the whole sector, right? The total loan losses, right? Total loan losses ratio. Right? So see this one again. So again, if we repeat this one, when we do the regression of the CNI uh, losses ratio on the total loans losses ratio, then we get this equation, right? The equation, and for the consumer loans or individual loans, we get this regression coefficient. So next time, uh, particular potential debtor that wants to borrow in a certain sector like consumer, for example, then you just put into the fact that the total loss ratio, right, is 15% so far. So you could guess that the loss rate, right, this is our conjecture, right, based on the equation. So conjecture would be 19.25% for the consumer sector. But again, we have a lot of course, we'll have a lot of discussion points on the robustness of the regression coefficients or regression taxes and so forth. But again, here we don't emphasize that part, but we simply use the regression technique to find some simple equations. Regulatory models, this will depend on the situation in every country. So I'll stop our discussion today here. Uh, so if you have questions, we can discuss further. Right? Hey, thank you. Thank you very much for tuning in today. I will see you next time with like other topics. See you. Bye.